Hi everyone, welcome to the video lecture for this week's module, which is based on modeling uncertainty. So in the business world, even in our regular day-to-day lives, uncertainty is a common phenomena and it's always going to be present. And as decision makers, especially as business decision makers, you have to spend a lot of time trying to plan for and respond to uncertainty. Examples for that include demand for your product being uncertain, or the time of the shipment of your inventory being uncertain, or if you're launching a new product, how will your market react to that product, or how will the competitors react to that product? That's going to be uncertain. So we need to figure out a way to incorporate that uncertainty into all our analytical models and decision-making processes. And that's where we bring in the concept of probability theory, which is what we're going to focus on for today's lecture. So we would have to revisit some of the common definitions and some of the common probability laws, which is what this video is going to focus on. So let's start off with the first definition, is how we define a random event. A random event is an event which involves uncertainty in a way that the outcome is unknown. So a simple example for that is, let's say the coin toss is going to be a heads or a tail. But what I do know is there are only two possible outcomes, which is a head or a tail, which is what we define as the sample space for that particular outcome. So let's write this down over here. Let's define A as the event of outcome of a coin toss. Now, in that case, the possible outcomes are a head or a tail. So the sample space for A is going to be defined as heads or tails, and this is usually denoted inside curly brackets. Similarly, another example is, let's define another event B as the throw of a dice. Now the sample space for this new event that we just defined is going to be 1, 2, 3, 4, 5, and 6, all the possible outcomes of the throw of a dice. That's how we define a random event and its corresponding sample space in probability. Now, another common term that you're going to come across a lot in probability theory is called the complement of an event. Now, the complement of an event is all the outcomes that are not in the event. So let's take the same example of the throw of a die. So we defined event B as the outcome of the throw of a die. Let's define a new event C. We're calling this new event C, and this is that the outcome of the throw of the dice is even. So the sample space for our new event C is given by 2, 4, and 6, all the even outcomes of the throw of a dice. Now in this case, if I have to define the complement of C, then the complement of C would be defined as all the outcomes that are not C. So the sample space for the complement of C would be given by 1, 3, and 5. So in that case, if we combine the sample space for C and the sample space for the complement of C, we get the sample space for the throw of the die, which is us to the next law in probability, which is called the addition law. Now the addition law is defined as the union of two or more events. And the way it's mathematically denoted is that if we want to find out the union of A and B, two random events, we have to sum up their probabilities and subtract the probability of their intersection. What this means is that we're trying to avoid any double counting, so there could be outcomes which are common in both A and B. So by subtracting the probability of those common outcomes, which are denoted by this intersection of A and B, we are avoiding double counting. Let's take an example to understand what the addition law means. Let's use this simple example to understand what the addition law means. So we're defining two new events. The first event is A, and the sample space for A is 1, 4, 6, and 7. These are all the possible outcomes for A, whereas the sample space for B is 3, 4, 5, and 7. If we need to find out what the probability of occurrence of both A and B is, then in that case we're essentially trying to find out the probability of A union B, and that's how we would denote it. So event A and B occurring at the same time, and mathematically that's denoted by this symbol over here of U, and that's how it's written. Probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B, which is denoted by the symbol of an inverted U. So the reason why we have to subtract this intersection is clear from this example here, that event A and B have some common occurrences as well. So 4 and 7 are two outcomes which are common in both A and B. So event 4 and 7 are basically the results of A intersection B. So the sample space for A intersection B is given by 4 and 7, and in order to not double count 4 and 7 in this whole sum, we have to subtract the probability of A intersection B from that event. However, there could be events which do not have any common occurrences. In that case, this intersection term becomes 0, so you just essentially end up with the probability of A plus the probability of B and no third extra term. Such events where no occurrences are common are referred to as mutually exclusive events. So if I refer to certain events as mutually exclusive, it just means that they cannot occur at the same time because they do not have any outcomes that are common between the two events. Next, we're going to talk about independent and dependent events. So the way dependent and independent events are defined are as if two events A and B do not affect the probability of each other's events, then they're classified as independent events. However, if the probability of event A changes if event B happens, then they're defined as dependent events. And for dependent events, we define a term called conditional probability, which means that if two events A and B are dependent on each other, this means that the probability of A, given that we have information that B has already happened, is going to be different from the original probability of A. Let's work with this example over here that I have on this table. So this is data taken from the sample of bank's records on how many of its customers have defaulted on their mortgage payments and how many have not defaulted on their mortgage payments. An additional piece of information that we have in this case is whether or not the customers were married or single. So let's move on to Excel to elaborate on how to calculate conditional probabilities with the help of this example. Okay, so now we are here in Excel and we have this table where we're given the number of customers for a bank where the customers are either single or married, and we know whether how many of them defaulted and how many did not default on their mortgage payments. So we're going to do something called converting frequencies into probabilities. And that's what we're going to do with this table here. I'm simply going to copy this and paste this here again, but instead of these numbers, I want the probabilities to be demonstrated in this case. So I'm going to convert this frequency into a probability. What I'm essentially doing is I'm saying that 64 out of 300 are married and they did not default on their loan. So the probability of a customer being married and not defaulting on the loan is 0.2133. Similarly, the probability of a customer being single and not defaulting on their loan is given by 116 divided by the total 300, so 0.386. And finally, the probability of being single and defaulting. And what you can see here is that my totals are automatically updated because they have the formula fed in them, and my total overall probability is equal to 1, which shows that my model here is correct so far. So let's just reduce these decimal numbers. So I'm just going to keep 2 decimal places here, and the way I'm reading this table is that the probability of being married and at the same time defaulting on your loan is given by this number here, which is 0.26. And this is the intersection term of being married and defaulting on the loan. Similarly, the probability of being single and defaulting on the loan is given by this number here, 0.14. Now, these are the intersection terms for these two particular events. So in this case, the event whether the person defaults or does not default is sort of dependent on whether or not they're single or married. So if we want to find out the conditional probability that a person has defaulted, given that we know that that person is married, is going to be the conditional probability of event D, conditional on the information that we know about their marital status. And if this probability is different from the probability of defaulting, which is given by 0.4, then we can say that events M and D are dependent on each other. So let's calculate the conditional probability of D given that M is known. So since the probability of default is 0.4 and the probability of M and D occurring at the same time is, now that we know that the probability of the intersection of events M and D, S and D are non-zero, which means that they do have common occurrences, and we know the probability of defaulting is 0.4. We're interested in finding out if the information about marital status is going to change our probabilities of predicting whether or not the customer is going to default on the loan. So what we're interested in is finding the probability of defaulting given that we know that the customer is married. So this is going to be the conditional probability of D given that event M has already happened, which means we have information that the customer is already married. Does that change the probability of defaulting? To do that, we're going to use the formula for conditional probability. So the formula says, in order to calculate the conditional probability of D given that M, we have to divide the intersection of D and M, so D intersection M by the probability of the event that happened first. In this case, that is event M. And since we already have these numbers for the probabilities, we're in a position to calculate that. Notice that the probability of intersection of D and M is going to be the same as the probability of intersection of M and D. So that number is given by this here, 0.26, and we're going to divide that by the probability of M, which is given by this total over here. So the conditional probability that the person is going to default on the loan, given that we know that the person is married, is 0.55, which is different from the total probability of default, which is 0.4, which means that if we know that the person is married, the chances of the person defaulting increases. So both the events D and M are dependent on each other, so if one event happens before the other, the probability of the other event is affected. Because of that same logic, now we're in a position to mathematically define independent events. Two events A and B are going to be independent of each other if the conditional probability of A given B is equal to the probability of A. So what we're saying is the probability of A does not change whether B happens or not. Now let's move on to the multiplicative law of probability. The multiplicative law of probability is that if we want to find out the intersection of two events A and B, we can simply multiply their probabilities if those events are independent, or we can multiply the probability of one event with the probability of the conditional probability of the other event. So if the events A and B are dependent on each other, just like the previous example, default and marital status were dependent on each other, in that case we would multiply the conditional probability of one event with the main probability of the other event. And if those events were independent, then we would multiply those probabilities together. This leads on to the Bayes theorem, which is the fundamental theorem for any artificial intelligence and adaptive learning algorithms that are used in analytics and data mining, is that we can calculate the conditional probability of one event given that the other event has happened by dividing the intersection by the probability of the event that happened first. What this does is it basically updates this probability once we have more information. So previously we had some information about A, which is how we got the probability of A, but then we found out more information about a related event B, and then we changed the probability of A given that we had more information about B.